So we are again going to be using our trig wheel to help us reason through our functions. So the first one, we're starting out with our function is going to represent the height of the dot above the horizontal diameter, so just like we did before, measured in units as a function of theta, the angle in degrees. So that is what is going to be new in this problem compared to the previous problem. So before we were using time as the input, we are now going to use degrees as our input. And then we're going to have our wheel still start from that 3 o'clock position. And then one other thing I changed is now we're going to assume that our radius is 1 unit. Okay, so using our circle here, we're going to think about the degrees at each of those key time frames. So at the 3 o'clock position, we are going to be at 0 degrees. At the 12 o'clock position, you can see that the circle has rotated 1/4 of the way around, which means that it is 90 degrees. At the 9 o'clock position, we've gone halfway around the circle, which means we will be at 180 degrees. Next, at the 6 o'clock position, we are 3/4 of the way around the circle, so that brings us to 270 degrees. And then last, when we get back to that 3 o'clock position, we are at 360 degrees. So the idea is that each time we go to that new clock position, we are adding 90 degrees. So we're going to keep spinning our wheel. So this means we are 450 degrees around, 540, 630, and then back at our 3 o'clock position, we are at 720 degrees. All right, so I've got this ruler here. We're going to go back to the ruler being at the horizontal diameter. The ruler is hard to keep steady, so I'm going to go ahead and just on the screen put in this horizontal line. All right, so when we are at 0 degrees at our 3 o'clock position, that dot is right on that horizontal line. So that means that we are 0 units above the line. At the 90 degree spot, or the 12 o'clock position, we are going to be 1 unit above. So remember, we changed our radius to be 1 unit, so that's why this is 1. At our 9 o'clock position, we are going to be back at the horizontal line, so at 0 units above or below. At the 6 o'clock position, or 270 degrees around, we are going to be 1 unit below that horizontal line, so we're going to write it as -1. And then when we are back at our 3 o'clock position, we are back at the horizontal line, so we're 0 units above or below that. And then we keep spinning around on our circles. So here we're at 1 unit above, back at 0, 1 unit below, and then back at the horizontal line. So this right here gives us our table of values. So just like before, I want you to, in a second, pause the video and plot those points. Make sure you label your inputs and outputs. Remember that our input is now in degrees, not in time, so make sure that's reflected on your graph. And then it also will have the same concavity as our previous function because we're looking at the vertical distance. So go ahead and pause the video to create the graph. Okay, so this right here should be what your graph looks like. Again, make sure that the input is the angle measure in degrees, right? So it's not in time. And you will see that this is still our sine function. So we have y equals sine, and then our input is in degrees. The symbol that we use for the input is going to be that theta symbol. And so that's what we will use for our input variable. Okay, so now we're going to go ahead and think about the unit circle. I've already got that drawn here. And we're going to label the points where it crosses the x and the y axes. So what we mean by that is right here, this point at our 3 o'clock position, that is going to be, since our radius is 1, so this is still a continuation of that previous problem, our radius is 1, So that means that we are 1 unit to the right and then 0 units above or below, right? So think about this if it was on like a coordinate plane, it would be the point 1, 0. Let's go to our 12 o'clock position. So this point, the x value is going to be 0, and then the y value is we are 1 unit above. So that would be the point 0, 1. All right, and then if we go to our 9 o'clock position, we are 1 unit to the left, and then 0 units above or below. And then the 6 o'clock position, this point would be 0, -1, because we are 0 units to the left or right of our origin, and then we are 1 unit below. Okay, so this right here is our general unit circle, and I've labeled those 4 key points when we have a radius of 1. So this is referred to as the unit circle. All right, so let's talk about some conventions that we have for working with angles. So we always measure angles with respect to the horizontal line. So that means that we are always thinking about starting from this line right here that leads out to our 3 o'clock position. And then also conventionally, we will be going in a counterclockwise direction. The negative angles will represent going in a clockwise direction. Okay, and then the last part is large angles, meaning that they're greater than 360 or less than 360, is just meaning that we are going around and around in the circle. So just like on the previous problem up here, notice we got to 720 degrees, and that's because we made 2 full revolutions with that wheel. All right, let's go ahead and move on to a different type of function. So we're going to change this up quite a bit here. We're going to now let our function represent the dot's horizontal distance to the right of the vertical diameter, right? So I underline that so that we are seeing what the difference is from the previous problem. We're going to measure the units as a function of theta, the angle, measured in degrees. We're still starting from that 3 o'clock position, and we're also assuming that the radius is 1 unit. Okay, so if we look at our wheel here, I've got the ruler. Notice that it is not horizontally placed, it is now vertically placed. And that's because we're going to be looking at the dot in relation to the vertical diameter. Okay, again, I'm going to replace the ruler with this vertical line on the screen. Okay, so let's go ahead and we will start with our table. And the degrees have not changed, and nor do the key points that we're looking at. So we can just go ahead and quickly fill in this table. So we're at 0, 90, 180, 270, 360, etc., all the way around. All right, so now we're taking a look at the dot in those same positions, but again, comparing it to this vertical line. So at the 3 o'clock position, here you can see that the dot is 1 unit to the right of that vertical line. So that means that our output is going to be 1 in that 3 o'clock position. Okay, next, if we move to the 12 o'clock position, notice the dot is right on that vertical diameter. So that means that we are 0 units to the right of that vertical line. At 180 degrees, that means we are at the 9 o'clock position. And notice the dot is to the left of our vertical line. So that means we are -1 units away from that vertical line. So meaning we're 1 unit to the left. Moving to our 6 o'clock position, our dot is right on the vertical diameter, so we're back at 0. And then the 360 means we're back at our 3 o'clock position, and we are going to be 1 unit to the right. And then we keep going around the circles. Okay, so now we're at 450 degrees, which means we're back at that 12 o'clock position. We are right on the diameter, so that's 0. 540 means we're at the 9 o'clock position, so we're 1 unit to the left. 630 means we're at the 6 o'clock position, so dot is on the line, and then here we are back at 1 unit to the right when we are at 720 degrees, so 2 full rotations. Okay, so this right here gives us our table. Okay, just like when we first started creating our sine function, we are now going to be creating a new type of function. So we're going to think about what this new function is looking like, and we're going to use some of the same questions that we saw on the first worksheet. Okay, so we are going to explain how the dot's horizontal distance to the right of the vertical diameter change as the dot travels from each of these locations. Okay, so you can see here on the wheel, when we're at the 3 o'clock position and we're going to the 12 o'clock position, we went from 1 to 0. So that means that our distance is decreasing. Okay, so again, we went from 1 to 0, so we're decreasing. Okay, and then from the 12 o'clock to the 9 o'clock position, we are still decreasing. So notice on our table, we went from 0 to -1. All right, next we've got the 9 o'clock to the 6 o'clock position. And so we are going from -1 to 0. So that means that we are increasing. So we're moving to the right, just like on a number line. We are becoming less negative, so we're increasing. And then from the 6 o'clock to the 3 o'clock position, we are going from right on the vertical diameter, so 0, to 1 unit to the right. So that is also increasing. Okay, so in a little bit, we're actually going to do a formal graph of this, but I just want to do a quick rough sketch just for a little bit of a visual. So if we plot some of these points, so this right here is our 90 degrees, 180, 270, 360. So just a very quick rough sketch and plotting those points. So if we just follow this right here, we know that it's decreasing for the first segment, decreasing for the second, and then increasing for the next two. But remember, this is not going to be a linear function. So this next part of the problem is we're going to be looking at the concavity between each of those points. Okay, so that's what this next question is building to. Okay, so we're going to be looking at 2 portions of the circle. So we're going from the 9 o'clock all the way to the 3 o'clock position, but you can see here in the picture it is broken up into 2 different sections. So basically going from the 9 o'clock position to the 6 o'clock position, and then this here will be the 6 o'clock position to the 3 o'clock position. And what we're going to do is look at how the change is changing so we can determine the concavity. So just like before, I'm going to try my best here to break this into equal angles. I'm going to do the same thing with this other one. Okay, a little bit harder on the iPad than it is in paper pencil mode, but we'll do the best here that I can on the screen. So now what we're going to do is look at the changes in the horizontal distance. Okay, so we're going from this point to this point, but I want to look at that horizontal change. So this is that first horizontal change. Okay, and then going from this point to this point, we're looking at that horizontal change. So that's this line right here. And then going from this point to this point, we've got that horizontal line. And then going from this point to this point, we've got this horizontal line. And so we want to think about how are those lines changing? Well, you can see that those lines are getting larger, which means that the rate is increasing. And so because the rate is increasing, that means we are going to be concave up during that segment. Okay, and then we're going to go ahead and do the same thing from the 6 o'clock to the 3 o'clock position. So we're going to go from this dot to this dot right here. And again, I'm just focused on that horizontal line, going from dot to dot. And then from this dot to this dot right here, we're looking at that horizontal line. And then from this dot to this dot, we've got that horizontal line. And then the last 2 dots we've got this little bitty line. So if we look at those lines, you can see that those lines are decreasing, they're getting smaller. Okay, so since the lines are getting smaller, that means that the rate is decreasing. And since it's decreasing, that means that the graph is going to be concave down at that point. And if you don't remember the concavity, that's just a quick little refresher. Anytime the rate is increasing, it's going to be concave up. So increasing means concave up. Decreasing means concave down. All right, so then when we go, we'll formally draw it here in just a second. But if we look at the 9 o'clock to the 6 o'clock position, so that's going to be from 180 degrees to 270 degrees. We said that it's going to be concave up. So from this point to this point, we know that the graph is going to be concave up. And then from the 6 o'clock to the 3 o'clock position, so that means going from 270 degrees to 360 degrees, it's going to be concave down. So it's not linear between those 2 points. We're going to have this nice concave down feel to it. Okay, and then the other 2 sections, I'll just go ahead and tell you, it's concave down between 0 and 90, and then it's concave up between 90 and 180. And so this right here creates our new graph. Okay, so I want you to go ahead and pause the video and actually graph those. So make sure you label your inputs and outputs, label your numbers, and then draw the dots, and then draw those concavities. So go ahead and pause the video to do that. All right, so this right here should be what your graph looks like. So again, make sure that your input is the angle measure and it's in degrees, and then the output is now the horizontal distance in relation to that vertical diameter. Okay, so this graph right here is referred to as our cosine function. So we've got y equals cosine of theta. We use theta to represent the input or degrees, and because we're looking at the horizontal distance, that is our cosine function. All right, so we will continue working with this worksheet in the next video. See you then.